Hello, world, and welcome to ARM TV. ARM TV are regular live episodes that cover the most interesting disruptive technologies, trends facing developers in the near future. Our speakers are notable visionaries and innovators who delve into the latest technologies shaping the future of computing, their impact, and how to make them work for developers like you. My name is Robert Wolf, and I will be your host. And in this episode, we are thrilled to be joined by AWS Principal Engineer and Cloud Native Compute Foundation's ambassador, Phil Estes. Phil is a container technologies specialist, CNCF OSS maintainer, and a member of the Open Container Initiative Technical Oversight Board. Today, Phil will be talking to us about the ARM revolution in cloud native computing. That's a mouthful. We will discuss the evolution of open source and cloud native technologies, more specifically, how the solutions of these technologies help developers embrace multi-platform computing and the adoption of ARM. You also have the opportunity to submit any questions you may have for Phil in our ARM Developer Program Discord server. As you can see the link here below, please feel free to head on over there now. We will cover these questions in our Q&A section at the end of this episode. So, we hope you'll spend the next hour with Phil and I and learn the importance of multi-architecture containers, the benefits of developing for multiple architectures, and how embracing these quickly evolving technologies can help you take advantage of cost savings and improve performance when migrating your workloads to ARM. Now, I think without further ado, it's time to bring Phil into the call. So, hello, Phil. How are you doing today?
Great. Yeah, thanks for having me, Robert. Great to be here.
Excellent. Yeah, no, we're happy to have you here, and thank you so much for taking the time. So, did I miss anything in that introduction? Do you want to add anything about yourself or what you do?
Yeah, no, I mean that's pretty good coverage. I've been working in the field of container runtimes for about a decade. So Docker and the CNCF project Containerd. You mentioned I was a open source maintainer. So that's kind of been the last decade of my career has been focused in this area. I guess one thing to note is, sadly, it also reflects on my age, but I've been working in the field of software development for 30 years later this year. So that's a pretty big milestone.
If we're lucky, we'll all get there one day, Phil.
Yep.
Only if we're lucky, right? But no, I mean, that's great. It sounds like you have a great resume, a lot of experience at hand here. And so I hope that you all are just as excited as I am to kind of learn what you have to show us today. Is there any sneak peek or teaser you want to kind of like prime our viewers with, whether you're watching live or on demand? Anything you'd like to kind of let our viewers know before you dive into this presentation?
Yeah, I mean, if containers and that whole concept are new to you, other than maybe you think of like this shipping thing you see go by on a train car or on a big ship, definitely I won't have time to dig into all the history of how containers are kind of the shipping metaphor for how software is delivered today. But there's tons of online content that I've given and tons of other experts in the Docker and container ecosystem. So that's definitely something we'll be focusing on toward the end, just talking about how developers have adopted that technology and how ARM plays into that.
Well, this is awesome. I understand the presentation is roughly about 30 minutes. I have gotten a chance to comb through it, but I have not heard this presentation yet. So I am very excited to watch it. Phil, are you ready to go? Do we want to dive into this now?
Yeah, let's do it.
Excellent. All right. Well, I'll see you on the other side, my friend. Thank you so much. And look forward to seeing this. Thank you.
All right. All right. Thanks, everyone, for joining. It's a little different to give a talk without any sort of visual feedback. So I hope you're out there. I hope you're ready and interested. And we're going to dive straight in. I'm going to roll back the clock to a time of sameness, I guess we'll say. I'll subtitle it the era of x86 and then later 64-bit x86. And really, it's the PC era. So I don't know if you're old like me, you kind of saw this advent of the personal computer based around the x86 processor. There were lots of computers before that, of course, both sort of in the business side. You think of the early mainframes and some of the big companies that developed computing sort of in the very early era. But if you come up into the, I guess, mid to late 80s, early 90s, there was this advent, not just of sameness of CPU. Obviously, that was part of it, but really this advent of interchangeability. The PCI bus and clones and BIOS. All these things were similar enough that you could just buy. In the end, you could buy a cheap PC. You can install Microsoft Windows, and everything just kind of worked because there was this homogeneity about that architecture. And of course, the good thing about that, if you were born in the US and went to primary school, you learned about early inventions, the interchangeable part, the ability for a factory to now have the same part used in multiple different systems, and how that brought efficiency. There's an efficiency to sameness, and that made really the PC era explode, in that there was this commonality, this common CPU that everyone was building for. You could write software here, you could send it to that machine, it would still work. And so there was a lot of benefit to that sameness. And really another interesting part of this PC area that maybe started with the IBM PC, but followed on with Dell and Gateway and Acer and many others. It was really at this point that this revolution separated the developer from the server. And that if you think about earlier days and earlier eras of computing, you had to connect to that server system. I know when I joined IBM right out of college, our email setup was still a green screen to the actual server that had the mail, and so that was the interface. But now you could have a PC, the actual computer, on your desk, and you could be a software developer writing code and then shipping it off somewhere. And it was, again, built around this early x86 architecture that grew 386, 486 Pentium, and on through the families. And as it became more powerful, the PC essentially became the server. We built data centers with many servers, and this same CPU family was really the de facto architecture of that era, and has continued on for many decades since. But of course, that wasn't the only thing happening in computing through this era. The Raspberry Pi came on the scene and was a huge hit among hobbyists and those interested in sort of digging into the details of the operating system, and sort of edge devices became popular, and this whole idea of having sensors all around the world and on vehicles and buildings and in shipyards. And maybe at the back end they were talking to a traditional PC based server, but there were new CPU families coming with each of these sort of generations of whether it's Arduino or cell phones, and ARM was a part of that story as well. And developers who worked in these areas started to understand this idea of I have to cross compile to a target architecture, because my PC is an x86 and I have to compile my software so it runs on this embedded system or on this cell phone. And so SDKs and cross compilers, those developers in that space kind of understood that world and how to operate in it. A little bit more complicated than sort of the straightforward, I just compile my code and I put it on the server. So that's a bit of a whirlwind tour through kind of that PC era that really brought us to a new era of heterogeneity, not just with ARM. Obviously, that's what we're going to focus on today. But IBM was bringing even their mainframe technology to the cloud. Linux was bringing about this new commonality of operating system that supported many CPUs. And so, we're going to obviously look at a timeline, but there were others involved in, bringing PowerPC and Z and other architectures to the cloud as well. Obviously, I work for AWS, so Graviton is a big part of that story. It was launched in 2018 and has multiple generations of that since. Ampere also created various platforms, continues to develop ARM CPU technology, and more recently Azure, Google Cloud with Ultra, with Axion, Again, more innovation, more launches of ARM technology in the cloud. So again, coming out of not just the embedded space, but offering servers in the cloud that run ARM CPU technology. In the midst of all this, just as an aside, we talked about the PC revolution. Many of you know that developers today, Mac is a super popular platform for developers. I'm giving this presentation from a Mac. And when they transitioned to Apple Silicon, it became an easy platform on which you could build for a Linux ARM 64-bit target and make that very simple for developers to build for ARM. So all these things, all these innovations, all these launches really brought in this new potential to not just have x86 in the cloud, but ARM 64 as well. But you might be asking yourself, okay, that's great, but why? Why is that interesting? Why is it needed? Why would we do that? These are just a few, direct pulls from case studies, from blog posts, from press releases. But really, as many of us know, in an era where people are considering, their cloud bill and their impact on the environment, or how can I get more efficiency and performance out of the same set of workloads and capabilities that my developers are building. You can see that ARM, these are all obviously representative of either Graviton or the ARM platform in general. Huge impact to cost, to throughput, price performance, energy consumption. I won't read these all, but you can, see that there's a real significant impact that makes ARM attractive to a company that's looking to understand how can I do the same amount of work, but how can I spend less? And obviously, companies tend to think about how does that translate into revenue, or how can I use this platform to be more beneficial to my bottom line? And so that's really been the reasoning behind a lot of this innovation and work to bring ARM into the cloud. Now, these days, there's an elephant in the room. Everyone wants to know, well, what does this mean about, for AI? AI is everywhere. Everyone's talking about AI, and specifically, generative AI and the chatbots that have come alongside that. Well, ARM is also playing in that space. Obviously, just in essence of the need for compute, the price performance value of ARM is directly applicable to the needs of AI workloads. And so you saw all that innovation on the last few slides, more cores, more memory, makes ARM a great platform for AI workloads. And there's already existing partnerships with NVIDIA. Obviously, CPUs and GPUs work together in many cases in AI. And there's, as we talked about, with a focus on sustainability and efficiency, AI workloads are massive consumers of compute. And so the efficiency benefits of ARM can help AI reach some of its sustainability goals. Just a quick quote from AWS's machine learning blog about a year and a half ago. SageMaker, a popular service for machine learning and inference, announced that they were making SageMaker available on AWS Graviton. And they specifically mentioned these benefits, price performance, and efficiencies that come from using Graviton. So again, AI is part of this world of people looking for more efficient, price-performant places to run these compute-hungry workloads. Obviously, I'm an employee of AWS. This is a huge area for us where we continue to grow our offerings on Graviton. I won't bore you by reading through the instance types, and because it made such a nice grid, I didn't even add the new Graviton 4 instance types that are still in beta that are coming soon. Similar to other AWS offerings, you can choose, hey, I want general purpose, or I want to optimize for compute or memory or storage. And so again, AWS customers can make those same choices when using ARM as the platform. So we've walked through kind of the history of the PC revolution, the cloud coming to be and initially being built around x86, and then ARM's arrival and its availability across many different providers. But what does that mean for you? Say you're a developer. I like to think of developers as those who turn coffee into software. Let's talk about how this new world and how these new options really apply to you as a developer. Now, I already said I've been working in this space for 30 years, and I was going to joke that this was a picture from my first day at IBM, but no, this is like at least a few eras prior to me graduating college and joining the tech workforce. But we can all agree that how developers work over time has vastly changed, from this idea of being sort of directly in the server room to those ideas I mentioned about, the PC revolution allowing us to, and now today with the internet, work literally from anywhere. But where we put our software, where we deploy these applications has also been evolving and changing over time. So let's walk through that a little bit. I don't know if you were around in the era of sort of the tower PC, the tower server, even before kind of rack mount. People had their precious, server that maybe there's a sysadmin that sort of kept you from messing with it. And if you wanted to deploy software, you had to put it on this server, FTP. If people even remember FTP, you move files around and hope that, when it launches on the server, everything works okay. And if you've heard the term pets versus cattle, this is definitely more toward the pets era. I remember, dating my wife. We were at two different colleges, and email was kind of a new thing. And you actually logged into a Unix server and used a mail program, to write someone else an email. And so I remember she was a math major, and so each of the servers at her university, were the name of a famous mathematician or scientist. And so I get an email from like Euler.math, her university name, or Planck.math. So, people were naming their pets, so to speak, in that era. But we quickly moved, to the vast data center where it made no sense to kind of call the server by name. And now, we had racks and racks of bare metal servers, and we were coming up with new technologies to deploy them and monitor them. But even beyond that, this era of virtualization came out, and I don't know if you were, working in the industry when VMware came out, but it almost seemed magical, out of the box. I'm booting another operating system on top of my machine, and I can watch it boot, and now I can log in, and I'm running a totally different operating system there. But in the server room, this became a way to package more and more workloads and to not have them fight against each other because my database needed different versions of the OS or different libraries than my web server. And so virtualization, took over for a couple decades. But today we're going to talk, through most of the rest of this talk about containers. And there's some similarities. A lot of people, when containers first came out and were popularized by Docker about, starting a decade ago, some people said, oh, these are lightweight virtual machines. Well, no, they're not actually virtual machines, because a virtual machine, you boot an entire operating system. There's a piece of software, the hypervisor, like the picture here on the right, that is booting the operating system and then starting your application. And you might treat it like a full server. You might have many applications running. Whereas in a container, they're all sharing the same single operating system. And now you have a container engine that manages the starting of an application. And inside that package of a container, you simply have the application and its dependent pieces, a library, a text file, a configuration file. And so it simplified this idea of packaging. So let's dig into that just a little bit more. Again, the metaphor was based around the idea of a shipping container, that there was a standard unit that you wanted to package up and deploy. And so it really gave us this idea of a standard unit of work, which is, hey, here's my application that I want to deploy. And then you actually put it in this sort of wrapping, this standard unit of deployment, the container image. And this is the thing I can move around. I can put it in a container registry. And when my server needs it, it can pull it from the registry and run it on the server. And so this was a new paradigm that, again, was 10 years ago, 11 years ago, was brand new, at least conceptually, to many developers. But there was a young startup at the time who had been using this technology themselves to operate customers' workloads. And they really provided kind of the pieces that made it very simple to do this. All the constructs of containers had existed. The Linux kernel had the capabilities to isolate a process in various ways. What Docker did was provide this common set of tools to what they like to term build, ship, and run container images. So building them, assembling your software into this container image, shipping it, moving it to like a container registry so that others could use it, sharing it with your servers or sharing it with the world. And then also tools to run that container image. So whether that's on your laptop or on the server in production, they were providing this common framework. At the time, they also created a common registry they called Docker Hub. Now, many cloud providers today have the ability to share and store your container images. But at the time, Docker Hub was almost the single place initially to store and share these container images. And they were initially building all the popular open source software and all the various distributions. So it became very easy as a starting point to say Docker run MySQL or Docker run Redis or whatever tool was of interest to you, or open source project, database, web server, Nginx. You could do that because Docker Hub already was packaging that standard unit of deployment that had that piece of software and all its requirements already packaged for you. So this really brought in a new era, but it wasn't just about Docker and containers. Kubernetes is now celebrating its 10th birthday this month. And so if you're involved in the cloud native world, you've probably already seen announcements about birthday parties and celebrations to celebrate a piece of software that was used to now orchestrate containers. So it's one thing to build them and push them to a registry and be able to run a single container. But when you think about cloud computing, the idea of scaling and preparing for that next spike when you release your new product, the CNCF became an umbrella open source foundation that its main sort of anchor project was Kubernetes, but has grown to include many dozens of projects that are all related to how we deploy, orchestrate, and operate software in the cloud. So if you think about the CNCF, the arrival of Kubernetes, you marry that to what Docker provided, the build, ship, and run of containers. And it was also at that time that, we talked some about practices from, the pets versus cattle, the bare metal servers, the virtualization, practices had been evolving and developing. And so DevOps was also involved in this next evolution or revolution of coming to cloud computing and thinking about not separating so much the developer from the operational aspect of my software running in the cloud. And so marrying a lot of those concepts and a lot of tooling was developed to make this possible, and continues to be developed to help people think about how to operate software in a modern way in the cloud. So we've looked at kind of the history of how we deployed software, how containers came to be, but we haven't married yet this idea that the cloud contains multiple architectures. And now I have this idea of a container image. How can I do that for multiple platforms? So if we think about a simple command like Docker run Nginx and the colon and a tag. So 1.25 is a version of Nginx that I might want to run a simple web server. And of course, in the early days of Docker, when the focus was on x86, that meant that if I typed this command, it would expect to run the container image that was built for that CPU family. And so if I did that on another CPU architecture, I could expect to get an error, or something would fail, or the actual Linux operating system would say, hey, this is a mismatched binary. I don't know how to run it. People came up with ideas in those early days of, well, I can just name something with a CPU architecture. So for 64-bit PowerPC, I'll just name my image nginx underscore PPC64LE, the same version. And now when people want to run nginx on this platform, they just have to use a different image name. And, again, for ARM and what Golang calls that architecture, AArch64, maybe I could also just change the tag. So I can tell people, hey, you can still run nginx, but change the tag to ARM64 underscore and then the version name. Hopefully by now you can see this is kind of a mishmash and a mess of like, what will it mean when I want my users to run ARM and they're looking at a document that someone wrote who was on x86. And so in 2015, this was the quandary as Docker became popular and as ARM and Power and other architectures wanted to be involved in the same container revolution. We really needed to come up with a solution to this problem that meant you could follow the same documentation written for one architecture and it would work on others. What you really wanted was the ability just to type docker run nginx and it would run no matter what architecture you were on. So we came up with a solution for that around April 2016. I wrote this blog post called A Big Step Toward Multi-Platform Docker Images. And it was when we launched a new version of the image manifest for Docker. It was called version 2, schema 2. And it added a new object type called a manifest list. And in a manifest list, you could list all the platforms that your image supported and pointers to where to find those image layers. And again, there's some deeper concepts there. You can go search on multi-platform and manifest list. And what became under another moniker, the OCI index, when all this was standardized under the Open Container Initiative. You can dig into a lot more details that we don't have time to go in today, but this was really a big moment of, okay, now we can actually build images that behind it support all the platforms that you want to support, whether it's ARM or PowerPC 64 or S390X or even Windows, because Microsoft brought support for containers to Windows OS as well. Another big milestone along the way was about a year later, all the official images. So I talked about Docker Hub and how they were already packaging many of the common and popular open source projects as container images. About a year, as I said, a year and a half later, all the official images were provided via manifest list. So now you could get to that point where you could type docker run nginx on whatever platform and it would work because it would pull the right image for your CPU platform architecture. So these were kind of exciting days of developing and providing this new capability, and really enabled kind of a new era of allowing containers and then the platforms that orchestrate them, like Kubernetes, to have clusters that included machines of different architectures. And there were a lot of great demos back in this era. You can probably find a ton on YouTube of people running on everything from Raspberry Pis to servers in the cloud using these multi-platform images. A quick dive into, I talked about some of the concepts, this idea of a manifest list or an OCI index. At the time, obviously, we were developing this. I wrote a tool to try and give a simple visibility into an image. So you run it, you give it a container image name, and in this case, hello world, which is a popular Docker image you can use to test that your Docker engine is working. All it does, obviously, in software, people love to write the hello world in a language that just says hello. And so in this case, the tool tells us, yes, this is a manifest list. Here's all the platforms it supports. And as you can see, Docker and the container ecosystem have added support for tons of architectures, and several of them are ARM. And that's because in ARM, there's versions of the ABI. And so whether you're on a Raspberry Pi or a 64-bit Graviton chip, everything from V5 to V8 is supported, as long as the person creating that image built variants of the image for each of those architectures. And if you know about ARM, you know that there's V9. We're currently working to add that definition. Again, we have to do that in the Open Container Initiative image spec. So there's a specification now that everyone uses. And you can actually see that type there listed, the OCI.image.index type. So that's where we define these platform definitions. And so V9 will be added there as well. And again, as I said, even Microsoft Windows has container capabilities today. And so you can support not just Linux, but Windows architectures as well in a multi-platform image. So this is all great. We've gotten to the place where you can build, ship, and run for multiple platforms, including ARM. But obviously the developer, the old adage is that developers are lazy. They want, tools that make this easy. You don't want to have to download new tools or learn new processes. And so more recently, Docker Desktop added support in a partnership with ARM, so that in Docker Desktop, which is a convenient tool, whether you're on Mac or Windows or Linux, to do these steps of build, shipping, and running containers and container images. And so this was another step towards making it easy for developers to adopt ARM by building the feature into Docker Desktop. So as I'm writing a piece of software and now I build it into a container image, if I'm using Docker Desktop, I can easily build for both ARM and 64-bit x86 and push that to a registry, and Docker Desktop does all of that for me. Again, making it simpler, not having to download new tools or learn new ways to build those container images. So we mentioned about the CNCF, that it's a host of many, many projects. And if you think about it, we've talked about the developer who's building software, but anyone who's building software today knows that, my software builds on some dependencies and some other libraries and some basic, image capabilities that I don't write. Someone else writes those. And the CNCF obviously is a place filled with projects that enterprises and developers are using in the deployment and building of their software. And so one of the things the CNCF has done in recent years is to enable member projects to enable 64-bit CI. So when that project wants to build and ship a release and run their tests, you want to validate. If you want to say, hey, my project supports ARM64 as well as x86, then you want a way to build that and be sure that you're testing it and fixing any bugs that might arise on a different platform. And so I've quickly screenshotted a few big announcements over the last year or year and a half. Ampere was involved in this. Actuated, which is a consultancy run by a friend of mine. This is one of his blog posts here, the state of ARM CI for the CNCF. I just talked to him the other day. He's updating this blog post already because many projects are using thousands of build minutes on ARM64 platform to validate that their CNCF project builds properly on ARM, runs on ARM, and all the tests. And when someone opens a pull request, the tests run. And so this is an amazing new capability that allows many of the CNCF projects to continue adding support for ARM64. Kubernetes does, Containerd, the container runtime project that I'm a maintainer of, we utilize Actuated to run testing on ARM64 on our platform as well. And so again, this is kind of that last mile that it's not just that my software needs to run on ARM. I need all my dependencies and all the projects I use. And so again, some of these things take years. And obviously, as you saw, we developed the sort of base technology to make this possible all the way back in 2016. But even now, we're still seeing the adoption and the growth and the ability to test and validate all the component pieces that people need to deploy their software in the cloud. And so that work continues. And the cloud operators, the CNCF, open source maintainers are all part of that adoption and growth that's happening. So kind of summarizing what we can do today, it's clearly possible now to build for ARM. You have been able to do that for a while, but it's now getting simpler. It's being built into tools, like I mentioned with Docker Desktop, to make it simpler for software developers to build and target and test on the ARM CPU family architecture. With the adoption of ARM64 and the CNCF, you can now orchestrate that software via the CNCF. You can use a Kubernetes cluster running against worker nodes that have ARM64 CPUs. And again, the ability to monitor and log and run your workloads with containerd. As projects continue to adopt ARM, that becomes easier to orchestrate. And then, of course, you can deploy on ARM infrastructure. Maybe you have a private data center, but as we've talked about, you can now do it on AWS, on Google Cloud, on Azure, via offerings they already have and support with ARM CPU architecture in the cloud. So kind of the call to action I wanted to make, because it's hard to know all the components of the audience that I can't see today. First, maybe you're just a developer and maybe containers are kind of new to you. Maybe using ARM64 in your project is a brand new idea to you. Well, you can install a container developer tool. Docker Desktop is a popular one, but there are many alternatives, including Finch that my team here at AWS has created, that's built around containerd and open source. Also supports ARM64. You can check out, more details on this image spec idea of, how we defined capabilities for multiple platforms. And then, Manifest tool is the tool that I built way back when, but people still use it to inspect and see what images support what architectures and to even assemble them and push them to registries. So if you're a developer, there's a lot of interesting things you can do to understand this platform, to understand how you can build for it, and potentially convince others in your company to adopt and use ARM. Do you maintain an open source project? Maybe you already support multiple architectures. Maybe you're a project that delivers container images, meaning that you expect your consumers to pull from a standard registry like Docker Hub. Obviously, be great if you could build multi-platform images so that people who are on ARM or PPC64 or any other architecture can use your project within their software deployment. Maybe you need to test on ARM64. You can check out actuated.dev that has the partnership with the CNCF. And there's also detail on works on arm.com that you can look at. And again, you can reach out to me as well, as we're a project, containerd, that's adopted ARM64 and can share our learnings. Maybe you're choosing a cloud strategy. Maybe you're not necessarily a developer, but you're trying to understand, hey, for the projects we develop, are we using ARM? Have we tested it? Have we done any price performance comparisons? So that's an option. You can check out, developer.arm.com. I'm sure Robert will have some potential starting off launching points for learning more about that. Obviously, here at AWS, we have a whole page about Graviton. You can read more of those case studies and information from people who've adopted ARM. And then, of course, you're going to want to validate vendor support. So if you're using other people's software within your deployment, you might have to check, are they support ARM64? So these are the kind of at least 3 call outs I wanted to make, depending on who you are in the audience. And again, I'll be in the Discord chat after the talk. If there's something I haven't covered or a pointer I can give you, I'm happy to do that. So with that said, it was awesome to have the opportunity to share this with all of you today. I hope it was useful, and I'd love to talk more. If you have questions, again, I'll be in the Discord after the talk, and we can chat more. So thanks so much.
Phil, what an amazing talk. I loved it. That was great. Very, cool. Very, I want to say very, covered a nice order of operations that I enjoyed. So, very, very cool. And, in fact, we did get some questions that came in. I look forward to kind of getting these to you. We do have quite a few people still watching, and I would like to remind everyone that is still watching, whether you're watching on Swoogo or on YouTube, feel free to post those questions. If you're in Discord right now, we are still watching the channel, so feel free to post those questions for Phil. We do have a few minutes here to cover quite a bit of them. So, Phil, I want to thank you. That was awesome. Let's get to this first question. This one comes from Konstantinos from our Discord channel. And he asks, how are sub architectures handled? Example, a Docker image with an app that supports SVE or SVE2, but not auto detection, SVE2 and ARMv9, but SVE is just an extension of ARMv8. Do we need multiple images in such a case?
That is an awesome question that, I promise I didn't pay Konstantinos for that, because we have it's very timely. We have a working group within the Open Container Initiative, which I mentioned. It's a group I've been a part of almost since the launch, that has standardized these ideas of what is a container image, what is a container at runtime, how do I define what program to start, what are the environment variables. The OCI has a working group that just launched in the last 3 months or so that's trying to answer difficult questions like this. Many of the participants come from the high performance computing space. And so anyone who works in HPC knows that there are way more variables involved than just the CPU platform. Kind of like your question here, there's a CPU feature, and if that's available, I want my workload to run there because I know it can take advantage of that. And if not, my software might crash because it depends on that feature. So they're trying to work out, they're not calling it sub-architecture, but essentially what are the variants or feature components that we need to add to container images to allow, again, the high performance computing space is a good example, because they have very specific clusters that may have very specific CPU features, and they use compilers that know how to tune for those features. So essentially, it's a bit of a non-answer because it's not a solved problem. Today people are sort of, for lack of a better term, hacking around some of these difficulties by using other features like labels and in the Kubernetes world, having node labels that you're going to match. And so, when you deploy this workload, you only want it to go to these nodes because they have that CPU and you compiled it for that specific use case. So we're hoping to solve that in a general way. It's kind of like the same problem we initially attacked, that Docker run Nginx couldn't work across architectures. So now we've solved that kind of big animal problem. Now we have the small animal problem of, well, I tune my image in a very specific way. How can I define in the image that I need that specific CPU or capability? So we're working on it, I guess, is the very short answer.
Awesome. Yeah. Thank you so much, Phil. I hope that covers it, Konstantinos. And, of course, Phil will be in the Discord a little bit later, probably about 15, 20 minutes or so. And you can get more elaboration or ask more further up questions on that, follow-up questions on that. I did share the link to our Discord and YouTube for those of you who are not already joining us in there. And Constantino says thank you in Discord. So cool.
Cool.
I have a question that's related to the trends of ARM adoption. You kind of did talk about some of this in your presentation, but maybe we could drill a little deeper in here. The question is, what are the most compelling reasons behind the rapid adoption of ARM architecture in cloud environments or cloud native environments? And how do you see these trends evolving over the next few years?
Yeah. So, like I mentioned in the early third of the presentation, we're in a world where, cost savings, efficiency, sustainability are all super hot topics for enterprises, for companies of all sizes, really. And so I think ARM kind of fits in a world where people are caring about price performance and about sustainability. That's led to, this, growing adoption in that space. What hinders that is obviously that it's taken us a while to make it easy to develop software, and containers have brought, ease to developers. I don't have to worry about the entire operating system. It's just my application and its libraries, and then multi-platform support. So I think, there's always that, long tail of, okay, but now I have this vendor thing I need and they don't run on ARM yet. So I can't, quite adopt it yet. So there's that aspect that I think as we see those being solved, we'll see even broader adoption. And then there's just the innovation, that timeline I showed, more CPU cores, more memory capabilities, as this CPU family and the people licensing it and building processors continue to grow, those capabilities will be incredibly attractive to people who need, whether it's AI workloads or whatever comes next. We haven't ever been in an era where we needed less compute. So that's really what we're going to see. I think is just that it will be a natural adoption curve because of the price performance and value of that.
Yeah, I remember. Great answer, by the way. I love it. And I remember dating back like 2018, I think it was, the first Graviton kind of starts getting announced, right? Or it gets released very soon after that. And the questions that developers had were like, will my workload run on ARM? Now it's like, how much will I save and how much faster will it be on ARM? And like, that's just in a period of like 5-7 years or something.
Yeah.
So, I mean, the questions that developers are asking are quickly evolving and becoming just kind of less about will it run and more about how much am I going to save and what am I going to, how much faster is it going to be. So that's really cool. And thanks to a lot of hard work from developers all around the world that are making this happen, of course. So talking about developers, let's talk about developer impact. How can developers at different levels leverage ARM technology to its fullest potential? Speaking of, to this topic, of course, at hand.
Yeah, that's a great question. I mean, the hard part of seeing developers as this, and they are a massive, millions of developers, is that they're all in some niche. There's front end developers who care about website performance and design of the front end, and there's
quick tangent. Is the full stack developer a myth? Like people who declare themselves, is that just a myth?
I think so, in the sense of like, it's, first of all, you go, you want to create a personal website. So you go dip your toe in like front end Twitter, and it's like, there's 17 new frameworks this week, that weren't there last week. So to think of yourself as full stack, to think of how you could be an expert in all the advancements at this end, as well as the back end, the databases, like, I feel like the complexity of the software world makes it very hard to be a true full stack developer. I mean,
master of none.
Yeah.
Okay, cool. Yeah, sorry for pulling you off topic there. I just had to ask you.
That's good. So, but with that diversity, it's hard to think, at each of those areas, there may be a very different answer about what it even means to adopt ARM. But if you think about the fact that, there's the idea of the back end of your favorite app, on your phone, has a set of software, maybe hundreds of services like, Netflix, and, there were early adopters of this idea. microservices. Anything that, again, I think all the things we just talked about really relate to that, in that they need to be in a place where it's not difficult to move all of those services and all their dependencies and the deployment software. All those things need to make adoption of ARM very simple, or else that friction is just going to keep them wherever they are right now, where it's quote unquote easy. So I think all the things that we're doing around container adoption, making it easy to build multi-arc images, getting the dependent projects that people are using for deployment, for orchestration, making that easy. Those are the steps that I hope will make it simpler for sort of the common developer, no matter who they are, to make it not, oh, I have to go learn this whole new set of things and tools to use this architecture that everyone says is so great. So simplicity and kind of the path, the adoption path, not having a bunch of roadblocks, is really how we'll reach a broader set of developers.
Awesome. Yeah. And I do think we're headed there. So,
Yep.
Yeah, definitely on the right path. Gosh, Phil, I have like 7 or 8 more questions and we don't have the time for it. I'm hoping, actually, maybe if you wouldn't mind, maybe I could share these questions with you and you could take some time to answer them, and maybe just post them in Discord later, if that's okay. It'd be cool to just give these answers somewhere. We do have time for 1 or 2 more here though. So, regarding performance and efficiency, you talked a lot about this during your presentation. In terms of performance and efficiency, how do ARM-based processors compare to traditional x86 architectures in cloud-native applications specifically?
Yeah, I think when we talk generally, it's a very similar impact. Cloud native involves both kind of some of the practices we talked about. I'm orchestrating my workload across a cluster of machines. It's scaling up and down based on workload. All of those aspects of cloud native are somewhat CPU agnostic. So it's really about my workload, my database, my web server. And that data that you saw on one of those slides applies. And again, it's imperative. If you're out there and say, well, nobody's talking about my special thing, my special sauce is a algorithmic, application that relies on this kind of CPU feature. Well, you need to test that with ARM and see if you get, the same kind of impact to performance. And some of those data points were about response time of my app, but essentially all those improvements are available to cloud native deployed applications because it's based on the workload simply performing better on that CPU and CPU family.
Yeah, there is a, what is it? You kind of don't know whether your workload, I mean, for the most part, you can kind of go in there and you can kind of assess whether your workload is going to see massive performance increases, massive savings, right? Like, or, just in general, whether or not the performance and efficiency is going to improve by migrating off of x86. But the more people who do migrate, it kind of becomes like an exponential value to everyone else, because then you end up with more stuff in the bucket, So I do think that if you're a developer out there considering migrating over from x86 to ARM, please feel free to reach out to me personally on Discord, and we can start hashing this out and figuring out whether or not your workload is in fact primed for this, or we can work together and figure out how to get it done. Let's get one more in here, and then unfortunately we're gonna have to close this out. But challenges and solutions. What are some of the biggest challenges developers face when transitioning to or integrating ARM architecture in their cloud native projects? And what solutions or best practices do you recommend? We kind of did talk about this, I think, in one of these earlier questions, but maybe we could just kind of like hash it out a little bit more.
Yeah. I mean, it really boils down to that problem of things can be simpler when everything's the same. So if I'm trying to develop a piece of software and I want it to be available on both x86 and ARM, we talked about Docker Desktop making it easy. I push a button, I get both built, they both get pushed. But, the nuances are that, it's software. And so the thing that you didn't realize is there's some part of your code that somehow when it's compiled for ARM creates this bug, this data race that you didn't have on x86. And so, there's a bit of complexity in, just having to figure out how to properly validate and test across multiple architectures, that maybe didn't exist when everybody had an x86 based laptop and all the servers were x86. And sure, there were still latent bugs and things that work different on, Pentium versus Xeon. But essentially, I think those are the challenges. Are that not everybody is sort of direct compiling to ARM64, so there's a cross compiler, and maybe in Go it works fine, but in Rust, there again some issue with the development of ARM support in Rust that causes something to break in your software. So yeah, I think those are the challenges. The solutions are tooling that makes it easier to test across these architectures, that make it easier to have your CI/CD pipeline, validate and make sure that your software is working the same on ARM. But yeah.
I love it, Phil. Thank you so much. And I did lie here. I would like to just squeeze this one last question in. It's a follow-up from Konstantinos. Your paid questionnaire. Just kidding. This one is, would there be a point for the concept of fat image, example, a single Docker image that supports multiple architectures or multiple flavors for a single architecture?
Yeah. So the only problem is I don't know whether we're talking about like not the old, but some of the concepts of like a unified image where the actual binary contains support for multiple, CPUs or architectures. The interesting thing is that many people initially called the manifest list, the container image format that I talked about, a fat image, because essentially it has a list of architectures that are supported. And when your container runtime talks to the registry, it says, oh, this is a manifest list. I got to figure out which one of these I can run. And so essentially, I think that architecture is really what we want to stick with, in that you can keep adding, we can keep refining that ability to add more images with more interesting components, like, like you talked about earlier. Well, I need a CPU that has this instruction set. And so, I think that idea of this manifest list, this list of images, and teaching our container runtimes how to match up the right image with what I'm running on the CPU family and specific architecture and sub-architecture. So I hope that answered it. But again, we can chat.
Yeah, I think he's going to be. I think he's going to be in there pinging you on
Cool.
this. Yeah. Cool. So perfect. Well, Phil, gosh, it was a pleasure. I feel like I could sit here for hours with you, and I hope I do get to eventually meet you at some point at an event. Maybe grab a coffee and pick your brain a little more.
Yeah.
But yeah, is there any last things you'd like to say? Call to action, send people somewhere to check out anything else. I know you mentioned some in your presentation. Of course, we'll include any links that were discussed in the description of the video later, but yes.
Yeah. I think most of the links are there. Again, if you're interested about this topic we've hit on twice here in the, about customizing an image for very specific features, head on over to the Open Container Initiative. There's that working group. They'd love to have more opinions, more people's thinking on how to solve this, because that is something that we're in flight. So yeah.
Awesome. All right. Well, Phil, gosh, a pleasure. Inspiring presentation. Great talk. Thank you so much. We appreciate your time. And we look forward to speaking with you more, and hopefully you'll stick around in Discord for the foreseeable future. I'm going to close this out now with your permission, if that's okay.
All right. Thanks so much for having me.
Excellent. All right. Well, on behalf of ARM and the developer program and those who were involved in making this ARM TV episode happen, we would like to thank each and every one of you for not only attending this event, but for helping us make this happen. Once again, a huge thanks to our guests. Phil Estes, thank you so much for being here. And as a reminder, be sure to check out the ARM developer program at arm.com/developer program and our developer hub at arm.com/developer-hub. There we go. Oh, the producer's on it. For continued learning and opportunities to contribute, please please head on over to the ARM learning paths as well. You can get access to that. Oh, right there. Look at that. We got the links there too. So we look forward to seeing you in our next episode of ARM TV. Y'all have a wonderful day, a wonderful week. Phil, we'll see you later. Take care. I hope you have a nice week as well. All right.
All right. Thanks so much.
Take care, everyone. Thank you.